Gauss's law. Consider a closed volume that's even oddly shaped, a blob. The idea of Gauss's law is surprisingly simple in concept, and it's that if an electric field is observed to be coming out of a volume, then surprisingly, all Gauss's law says is there must be charge inside. Now, the math of this gets a little more complex, but on the right-hand side, we have Q inside, the charge inside. The epsilon sub zero in the denominator, that's just a fundamental constant known as the permittivity of space. So this idea of electrical flux that we'll explain in a minute, electrical flux is proportional to the charge inside. Now, the flux relates to the surface area that encloses the volume. And we can zoom in on a small part of that area that I call dA, right? D is differential, right? So dA makes this an area element. Also, you might be thinking, hey, wait, area is a scalar, but I put the vector line over area. You can actually make area a vector if you assign its direction the normal or perpendicular to the surface, right? So dA is an area element that is the area of this little patch and direction normal to the area. In any case, the electric field arrow E is shown here at this little area element. And, this idea of flux is that we really need the perpendicular component of E, right? So flux turns out to be electric field times area. And it's really the perpendicular component of electric field at an area element multiplied by the area element. And that would be an element of this flux that we're starting to see here. So I have E perpendicular shown in red here and that little area patch. Let's zoom in on another. So here, another part of this surface area of a blob, we would have a different area patch, a different normal, different electric field. And again, our task is to take the electric field at that location and consider its perpendicular component, the component perpendicular to the area, or that is the component along the normal. And so that little perpendicular component and that little area are part of what we're discussing, right? So again, the concept is simple, that electric field coming out of a closed volume implies charge inside, but now we're getting lost in the details here that flux is basically electric field components perpendicular to area elements, and then the product of those summed up over the whole surface area. So symbolically, we would get this double integral, which don't worry about that. E dot dA just means the electric field component perpendicular to the area times the area. And that is proportional through 1 over epsilon 0, proportional to the charge inside. So flux is proportional to charge. Flux associated with a surface is proportional to the charge within the volume that is inside that surface area. Right, so the left-hand side is this concept, electric flux, right? Electric field times area. And instead of the calculus way of looking at it, it's easier just to say, all right, it's the electric field perpendicular to the surface area times that area. I just showed the earlier slides to show you how complex it really could be, that for a blob, electric field arrows could be going in any direction. Area patches can be oriented in all different ways. So E perpendicular times area is a little more complicated in practice, even though the idea is simple. And so in and of itself, Gauss's law is not very useful, right? We have this idea that the electric field coming out of a closed surface is proportional to the charge inside that volume. But there are some useful cases worth looking at least to see the theory. The point charge, where we will see that we get Coulomb's law from Gauss's law. We can also look at a line of charge, an infinite plane of charge, and two infinite and oppositely charged planes or plates, the parallel plate situation that is called a capacitor. So let's look at a point first, right? So we have a point charge Q. We need to, visualize a surface that would have a high degree of symmetry related to this point. Otherwise, as you saw with the blob, it would be impossible to figure out the flux in that case. But for the case of a point, a nice symmetrical shape would be a sphere, right? So this sphere is a hypothetical blob that has, the dotted surface area here and this enclosed volume. And what we would do is realize that electric field comes from positive charge, and it would sort of form this radial electric field line pattern, like so. And, along the area, the surface area of the sphere, notice that the electric field is always perpendicular to the surface, so that simplifies the calculation. We really only have to look at that surface area and say that the electric field E times the surface area of a sphere, 4 pi r squared, equals the charge inside Q over epsilon 0. Rearranging terms, we get the electric field for a point associated with a point, a distance r away, is 1 over 4 pi epsilon 0, which is actually the Coulomb constant K, times the charge over the distance squared. So we obtained Coulomb's law from Gauss's law. Let's move on to the line. Right, so here's a line of charge. And again, the key is to imagine what would be a surface area that is symmetrical with respect to a line. Well, how about a cylinder, right? So a cylinder such that the line of charge is along the axis, the central axis of that cylinder. Again, we would visualize the electric field arrows as going away from positive charge in all directions. And we would really only have to consider where the electric field is normal to the surface, and that's this annular part of the cylinder, right? The discs that are the, top and bottom, let's turn on its side, like the caps, they would drop out because the electric field would be parallel to that surface area. So only the electric field going through the annular portion of the cylinder needs to be counted. And so we would get 2 pi r is the circumference of a circle, times L, the length of the cylinder. That would flesh out the area of the annular part of the cylinder. So 2 pi r L times the electric field E is the charge inside over epsilon 0. Now the charge inside is the portion in the cylinder, and that's the linear charge density lambda times L. L's drop out. We rearrange terms, and we would get the electric field for a line of charge is 1 over 2 pi epsilon 0, the linear density lambda over R. Right, so a different formula and obtained from Gauss's law. Next, we would look at a plane. Right, so here's an infinite plane of charge. And again, we expect the electric field to be shooting away from positive charge. And we need to come up with a surface that has symmetry with respect to this plane. And actually, we could use a cylinder again, but it's oriented differently. And actually, it doesn't have to be a cylinder. It actually doesn't matter what the cross-sectional area of the shape is. In this case, it's a disk. As long as that, these end caps, the disks, are parallel to the plane, right? So when we're looking for flux, unlike the line case, the annular part drops out, right? Because the electric field is hugging the surface of the annular portion of the cylinder. Now, I'm going to stick with the cylinder, but it actually doesn't matter what the shape is in the cross section. But in any case, you can see only the electric field perpendicular to the end caps will count. So whatever the area of this cross section is, that times E on one side, and another electric field times E on the other side. So that's 2 times electric field E times the cross-sectional area A. That would equal 1 over epsilon 0 times the charge inside. The charge inside is the surface charge density sigma times that cross-sectional area. So if we solve for electric field, and the A's will cancel, and we get, for an infinite plane of charge, electric field is the surface charge density of this plane divided by 2 times the constant epsilon 0. And so that's another formula, again, from Gauss's law. So far we have Coulomb's law, we have a line charge formula, we have an infinite plane formula, all coming from this theoretical Gauss's law. Now the next case is parallel plates. And for parallel plates, we have 2 equal parallel planes of charge, equal in that they have the same surface charge density sigma, but one is positive and one is negative. Now we don't actually have to use Gauss's law. We already did Gauss's law for a plane. But by superposition, we can take the formula for 2 planes and combine them. And again, we expect electric field to go from positive and then to negative, right? So that would be our electric field pattern in between the parallel plates. Notice that in between the plates, we are simultaneously repelled from the positive and attracted to negative, both cases going to the right. On either side of the parallel plates, we would get cancellation. For example, over here, repelling from positive and attracting to negative, they cancel out. So the usefulness of parallel plates is that the electric field is contained within the plates. And I alluded to this earlier, but, okay, not infinite planes, but finite small parallel plates, ignoring any fringe effects at the edges, we have what's called a capacitor, the parallel plate capacitor. It's useful because the electric field is contained within the package, within the plates, and it actually temporarily stores energy, as we'll see later. In terms of the formula, we have a doubling up in the middle, right? So sigma over 2 epsilon 0 plus another sigma over 2 epsilon 0. We get a half plus a half as a whole. We get sigma over epsilon 0 for the parallel plates in between the plates. And we get no electric field either to the left or to the right of the parallel plates. So those were the useful cases. And here's a summary of the formulas. And again, something like Gauss's law, which is theory, at first it's just a concept, and then it looks kind of abstract. And you might wonder, well, why do I need that? And to some degree, I understand that you really don't. It's theory. But Gauss's law does yield this set of formulas here, whereas our empirical Coulomb's law was only the first formula. And just to connect the two together, Coulomb's law was kq over r squared, where k is the Coulomb constant. Sure enough, if you take the permittivity constant and evaluate 1 over 4 pi epsilon 0, you indeed get the Coulomb constant. So Gauss's law is very fruitful in giving us all of these formulas.